Okay, welcome. And now we're going to do the section on critical path algorithm. Okay, so a sequence of tasks in the diagram is called a path. Okay, so this is similar to what we talked about before with the Euler paths and the Hamiltonian path. So this is another type of path. In the previous example, we saw that the critical path dictates the minimum completion time for a schedule. Perhaps then it would make sense to consider the critical path when creating our schedule. Okay. For example, in the last schedule, the processors began working on tasks 1 and 3 because they were longer tasks, but starting on task 2 earlier would have allowed work to begin on the long task 6 earlier as well. The critical path algorithm allows you to create a priority list based on idea of critical paths. So critical path algorithm, this is version 1. Okay. It starts off with step number 1, find the critical path. 2, the first task in the critical path gets added to the priority list. Okay. 3, remove that task from the digraph. 4, repeat finding the new critical path with the revised digraph. Okay, so that's the steps we're going to use in the critical path algorithm. Okay, so let's do example number 4. It says, recall this is the digraph. Okay, for example 3. Okay, so it looks a little bit different, but it's the same digraph. Okay, so here's what we would do. This digraph has critical path 2, 6, 5, 8, 10, right? So in this case here, we have, so 2 gets added first to the priority list. Okay? So notice how we have 2, so if we go 2, 6, 5, 8, 10. Okay, so that this is the critical path. Okay, 2, 6, 5, 8, 10. So 2 gets added to the priority list. Then we remove T2 from the digraph, and so then we get this here. So T2 has been removed. Okay, so the critical path, which is the longest path in the remaining digraph, is now T6. 5, and then 8, and then 10. Okay, so now in this case here, we then add T6 to the priority list. Okay, oops. And now we remove T6 from the digraph. Okay, now, so now in this case, there are two paths with the same longest length, right? So we've got T1 here, okay, and then we've got T5, and then we've got T8, and then T10. Or we could do T3, T7, T8, and then T10. So they both yield the same number, which is 24. So those are the two longest paths. Now we can add T1 to the priority list, or T3. We usually add the one with the smaller subscript just out of construction and remove it. Okay, and then we continue the process. Now, when we're all finished, our priority list ends up being this. Now, searching for the critical path every time you remove a task from the digraph can be tedious, tiring, especially for a large digraph. In practice, the critical path algorithm is implemented by first working from the end backwards. This is called the backflow algorithm. Okay, so the way we would do that is the backflow algorithm works like this. Okay, one, we introduce an end vertex and assign a time of 0, shown above in brackets. Okay, so right here. We move backwards to every vertex that has an arrow to the end and assign it a critical time. 3, from each of those vertices, we move backwards and assign those vertices critical times. Notice that the critical time for the earlier vertex will be the task's time plus the critical time for the later vertex. For example, consider the segment of digraph. Okay, so we'll look at this here. Okay, let's look at this. So T1, 5, right? And T2, 4. Okay, I guess this is just in general. So here, if we look at this diagram here, okay, so if we look at just this diagram here, okay, so in this case, if the task 2 has already been determined to have a critical time of 10, which is in the brackets here, then T1 will have a critical time of 15 because you're going to add the critical time of 10 from T4 or T2 to the critical time or to the time that task 1 requires. Okay, so that would be 15. And so as you can see, that's what we have written here. Okay, now then step 4 says, if you've already assigned a critical time to a vertex, replace it only if the new time is larger. For example, in the diagram below, T1 should be labeled with a critical time of 16. So because look at here, we have T2 and T3, right? So T2 has a critical time of 10. T3 has a critical time of 11. Okay? And so in this case here, if we were going to assign a critical time for T1, we would use the larger value. So it would be 16, right? Because we would use the 11, not the 10. So this would have a critical value of 16, not 15. Now repeat until all vertices are labeled with their critical times. So now, once we have completed the backflow algorithm, you can easily create the critical path priority list by using the critical times you just found. Okay? So, let's look at critical path algorithm version 2. So this means that step 1, you apply the backflow algorithm to the digraph. And then step 2, create the priority list by listing the tasks in order from longest critical time to shortest critical time. So let's do an example, okay? Now, this version of the critical path algorithm will usually be easier to implement. Okay, so let's try it. So let's look at example 5 here. So we're going to apply this to our diagram from the earlier example by applying the backflow. So here we are. We start with the endpoint, right? So as a critical value of 0. Okay. Now from there, we're going to move back to the tasks 9. Okay. 9. 4, right? 9, 4, and 10. Okay, now the critical value for 9 is going to be what? 2, because there's nothing to add. The critical time for, or the critical value, or critical times for T10 is going to be 7, and the critical time for T4 is going to be 4, right? So notice how we have those brackets, right? Those are always going to be the same because you're not adding anything because they're connected directly to the end result, the end result. Okay. So now we go to those and see what's connected to these. So T9 is connected to T5. Okay, and that's the only one it's connected to. So we would add 5 to the 2, which would give a critical time of 7 for T5. For T10, we have also connected to 5, right? So 10 is 7. So 7 plus 5 is 12. Okay. And then what do we have here? Well, T3. Let's do T8. So T8 is 3. This is 7. 7 plus 3 equals 10. Okay? And then 10 plus 5 is going to be 15. And then here it's going to be 7 plus 5, which is 12. And then for T9, it's going to be 2 plus 5, which is 7. So the largest one is going to be the 10 plus the 5. So it's going to give us 15. So we're going to use 15 for T5. Okay. And now T10 is also, let's see here. Oh, T7. Let's look T7. T7 is connected to T8 and T10. So T10 will give a critical time for T7 of 7 plus 4, which is 11. And then T8 is 3, so it'll be 3 plus 4, which is 7. So this one is we're going to keep the larger one, so it'll be a critical value of 11. Okay, and then now what do? We now go to T6. Well, T6 has 10, but it's going to take the larger critical value of 11 or 15. So we're going to take 15 plus 10. So this is going to have a critical value of 25. All right. Okay, so now we just look at T6. T6 is going to have a critical value of 21. T2 is going to have a critical time, not critical value, critical time of 28. And then T3 is going to have a critical value of 18. Okay. Um, so let's see how we did. Okay, so according to this, the critical path should be, if we did this right, should be T2, T6, T5, T8, and T10. Okay, well, let's see how we did. Hold on a second. Why does it have a critical value of 14? Did I make a mistake here? Oh, wait a minute. That's right. This is 14 because I missed this one. T10, yeah, T8 is connected. How did I miss that? I don't know how I'd miss that, but yeah, this should be 14, not 11. I goofed. I used the wrong number. So 10 plus 4 is 14. 7 plus 4 is 11. I don't know. I don't know what happened there. So that should be 14. Nope. So that means this should be, that's still 25. So that's good. And this should be, instead of 18, should be 21. This should be 21. Okay. That should be 25, and then, okay, that's okay. This should be 21. Okay, so that should be right. So let's see what I did here. So that should be 0, 7. So this should be 10. So that's right, 10 and 12. Wait a minute. Why is that? Seven. Oh, there we go. Okay. So we got 21, 28, 21, 4. 21, 28, 21, 4. Okay, so I did do it right. Good. So it should be 15, 25, 14. 15, 25, 14. Good. And then we got 10. All right, so the only goof I made was I missed this one. So that was, which it caused, so I missed this one, which caused T3 to be incorrect. But you get the point. Okay, so again, be careful. You got to be very careful that you don't miss anything when you're going backwards. But that's basically how you would do it. And so, did it change the result? No, I don't think it would change the result. So it'd be 2, 6, 1, 3, 5. 2, 6. Oh, right. So the priority list is going to be based on going from largest to smallest. Okay, so notice how we go 2, 6, 1, 3, 5. So we go 2, 6, and then this is the next largest. And remember, we have two of them that are 21. So, well, here, I'm going to circle these. So we have 2, 28, and then we go to 25. Then we go to 21. There's two of them, so we go in numerical order by the subscript. And then 21, the next lowest is what? 15. And then we go to 14, right? And then we go to 10. And then we go to 7. And then we go to 4. And then we go to 9. So notice that that is the path. 1, 2, 2, 6, 1, 3, 5, 7, 8, 10, 4, 9. All right. And then applying the priority list that we just came up with, and we apply it with two processors, right? So we're going to do task 2, right? So task 2, and task 1, right? Those are the 2 that we would do first. These here. Okay. Notice how we assign them to the processor in that order. Okay, and then so these are processed. Okay, and then what happens when T2 is done? We assign the next one in the priority list, which is T6. So when that's done, right, T2 is done. When T2 is done, we go to the next one in the list, which is T6, right? That one has to be done first. So T2 is done. So then we're going to assign that one, right? And then when T1 is done, because T1 will be done before T6, we assign T3. Okay? Now, T3 okay. Okay, so notice how these two are going to get done at the same time. Okay, and so then we assign the next 2 tasks, because these will finish at the same time. So then we assign T5 and T7. T5 is 5 hours, T7 is 4, so 4 is going to finish first. So once T4 finishes, or excuse me, T7 finishes, then we'll assign the next one. So T7 will finish first. So then T8 will be assigned, or hold on a second. Where's T? So T7 will be finished first, and then so the next one that we can assign is T8. Or hold on a second. Oh, T4, right here, because it's here. Okay, so we can assign T4. Okay, that'll take 4 hours. And then while that's going on, the next task, T5, will finish up. Okay, so T4. So that's going on. And then T5 is finished. And when T5 finishes, we'll assign T8. T and T4 will finish at the same time, and that's when we assign T10 and T9. Okay? But again, take your time, make sure you understand how we use the priority list, because we're assigning it the same way we did before in the last example in the last section. Okay? So again, make sure you use those steps to keep track of everything as far as setting up this schedule. Okay? And again, it would look different if there was 3 processors. Okay. So again, in this particular case, we were able to achieve the minimum possible completion time with this schedule, suggesting that this schedule is optimal. This is certainly not always the case. All right. Now, let's look at example 6 here. It says this example is designed to show that the critical path algorithm doesn't always work wonderfully. So schedule the tasks in the diagram below on 3 processors using the critical path algorithm. Okay. So now, this is weird. There's no lines here. Okay, maybe interesting. Okay, so we're going to use the backflow algorithm. Okay, so notice how we did this. So again, just to make sure we did this right. So we've got 6, right? So this is going to have so these are all end processes. So this is going to have a 6. This one's going to be 6. So again, these are just individual tasks that are not connected. So this is going to have a task of 6. And this is going to have a task critical time of 1. Okay, so those are the ones that we have. Okay, so based on this graph. Okay, now if we look at T6, this is going to have a critical time of 8. Right? 6 plus 2 is 8. And then T7 has a critical time of 8. And then T8 also has a critical time of 8. And so since they're all the same, T1 is going to have a critical time of 9. Oh, and then I missed T2. So T2 also has a critical time of 1. And so here, this is what we have. So now based on this, we go from largest to least. So it'll be T1 followed by T6 and then T7 and then T8, right? No particular order, but we usually go in increasing subscripts, right? And then from there, we have T4, T5, and then T9. Those are all 6s. And then followed by T2, and finally T3. So that is how we do our priority list, our critical path priority list. And then from there, this is how we use to do our schedule. Now with 3 processors, notice that we apply T1 to processor 1, and then we apply T4 4, right? Because again, larger, so T1, and then we do T4, and then we do T5. Okay, so those get done first. And then from there, we're going to assign T6, which has a value of 8, because now it's ready. So a value of 8. Okay. And so that's going to take 2 hours. So that's going to finish up. And then what happens here is then T6 is going to finish before T4 or T5. So now we have T7, which is the next one that we're going to assign. Right? And then T7 is going to finish before T4 or T5 finish. So that by that time, we're going to do T8 for 2 hours. Well, then 4 and 5 are going to finish at the same time. So now we assign what? The next two tasks, which are going to be T2 and T3, because they're the next priority. So we have 3 and 4, right? Because of their position. And then those are going to finish up, and the last task that we would assign is T9. Okay, and now here's the thing. Is this the best schedule? No, it's not, because you can easily switch things around and come up with a schedule that would end sooner. Like, for example, when these got done, you could have, at this point here, they all get done at the same time, or hold on a second. T7. Right, so you could have assigned, when T7 was done, you could have assigned, or when let me see, T7. Could have, where you could have switched T6. Right, you could have assigned maybe T2 and T3, right? See? And so that's what they did. So if you assigned instead of these, you could have assigned these T1, and then what would happen? These would have finished at the same time for 1 hour, and then you could have assigned what? All three of these tasks, T6, 7, and 8. And then you could have assigned task 9, 4, and 5 at the same time, and we would have gotten this. So we would have shortened the time from 13 hours to 9 hours. Okay? So in most cases, the critical path algorithm will lead to a very good schedule. There are cases like this where it will not. Unfortunately, there is no known algorithm to always produce the optimal schedule. All right, that's it. So thank you for listening, and that wraps up this section and this chapter on scheduling.